Good morning, beautiful babies. Okay, today we are going to be going over the Force and Motion Study Guide. You are here with Miss Ross's Core 1 class. Everybody say hello. Hello. They're so beautiful. And they've had breakfast and they've had music class, so they are ready to give you intelligent answers. Here we go. Put your name on your study guide. At the end of class today, after we have gone over this study guide, please don't come to me and say, Miss Ross, what should I do with my study guide? Take it home and study it. Are you ready, Zahia? Here we go. This is a speed graph. If you want to know speed, write this down up here. If you want to know speed, what are the two things you have to know to find speed? Tell me, Emily. Very good. You got to know the time. And you got to know the distance. That question will be on your EOG as sure as Miss Ross is sitting here in the squeaky chair. All right. So it says, number one, the graph above shows the motion of a woman riding on a bike. So she starts off at a steady pace. She stops for a couple of seconds, a couple of hours. Then she keeps riding again, riding faster this time. Then she stops for a little bit of time, and then she comes back to the start where she started from. Does that make sense? Okay, here we go. For which period of time was the woman's speed the fastest? What was that word I used yesterday that I said, if it is this, it is fast? Remember we had a little mini lesson. What was that weird word, Layla? Do you remember? Started with an S. Levante? Steep. Good. If it is a steep part of a line, that is the fastest. Where is the fastest part of this line? I'm going to highlight it in pink. The fastest part of this line is the steepest part of the line. Do it right here. This would be the fastest because from 8 to 12 hours, she went 3 to 12 miles. So she went 9 miles in that section because this was 3 and this is 9. No, sorry, this is not 9. This is 12. So in that time period from C to D, she added 9 miles to her distance. So down here, you're going to write from hours. C is at 8 hours and D is at 12 hours. So from hours 8 to 12. All right. During which two time periods was the woman stationary? What does stationary mean, Malachi? You're stationary right now. What are you doing? Yes, he's sitting still. All right, so in the time periods that he's sitting still, I am going to highlight those in red, like stop. This is sitting still, and this is sitting still, this part right up here. Janie, from B to C, what hours is that? Yeah, about 4 to 8, I would say, or 5 to 8. I think since it's like in between 5 and 6, we could say 5, right? That's 5 to 8 hours. And then this section right here is between 12 and, what'd y'all say? 14? Yeah, 12 to 14. So from 5 to 8, and from this D to E section, this is from hours 12 to 14. All right, those are her two stationary sections. All right, during what time period was she coming home? Evan. So what was the letters that goes with coming home? Yeah, there's letters here and here. What were the letters? Good. From E to F, she came home, right? Highlight that here. This is CH coming home. She returns to the starting line. So that was from hours 14 to 20. Because the E is here, 14, and 20 is there. So from 14 to 20. So when she first started, how long did she bike before she took a break? What do you think, Sydney? So this section right here is where she was riding at first. How long did she ride before she took a break right here at B? What do you think, Sid? Yes, she rode for 5 hours before she took a break because she went from A to B, which corresponds with 5 hours. B corresponds with 5 hours. All right. Next question. Now we get into the easy ones. All right. A pencil falls off a desk. What makes it fall to the floor? Zahaya, what makes it fall to the floor? Gravity. Write it down. Gravity. Next one. What causes a ball to move through the air when it is thrown? What causes a ball to move through the air when it is thrown? No, you were about to say it. A push. I'm pushing it. What's that called? There it is. A force is a push or a pull. A force. Because you are literally pushing it. Write that. Force is a push or a pull. Either way, that is how a ball moves through the air. How can the speed of a ball best be determined? What 2 things do you need to determine speed? Janie. Very good. You take the distance. Write this. You take the distance and you divide it by the time. Distance divided by time. But you gotta have the distance and you gotta have the time if you're gonna determine the speed. All right. We're going to talk, I want you to describe balanced and unbalanced forces in relation to tug of war. What's happening if the rope is not moving? Write this down. If it is not moving. Levante, what's happening if the rope is not moving? Is it balanced or unbalanced? Balanced. Good. If it's not moving, that means that it is equal and opposite. Balanced means it is equal and opposite. So they're pushing or pulling in opposite directions and the force is the same. What about if you guys go up against Miss Letchworth's room? Yeah, you're losing. That's right, Levante. You are totally going to lose if you go up against Miss Letchworth's class because I have seen those kids. They are some big children in there. I don't know what they're feeding them, but it is something that makes them grow to large sizes. They are very large children. So if we go up against them, is that going to be balanced or unbalanced? It's totally going to be unbalanced. You guys are going to get rocked. Those kids are going to throw a hurting on you. All right. So if they are moving, if it is going to be moving, it is unbalanced. Some might even say unfair. Because how are we going to win against that? I don't know. No, look at them next time they come out the door. There's not just 2 big kids. Yeah, they are some very tall children as well. They're very tall.
This is starting to get offensive.
Okay, I'm sorry. I'll stop quiet. Okay, look, I can say that I can talk about short people because I'm short. Okay, here we go. Miss Schaefer was walking her dog, and then suddenly her dog wanted to run. What would happen to her? What would happen to her? Okay, so she's holding the dog on a leash and the dog jerks forward. What is going to happen to Miss Schaefer? Tell me, Emily. right. She's going to jerk forward, right? And then what's going to happen? Here? She's going to get pulled. Very good. So inertia will jerk her forward. Then her speed will increase as she is pulled forward. So she's going to get that, she's going to have an initial jerk, and then she's going to be pulled forward. All right. Why would you want to increase friction? Talia, why? Why might I want to increase friction? Y'all make the noise with your shoes. Do it. Why do I want that, Talia? Why would I want to increase friction? What'd she say? There it is. She said, so you won't like slide everywhere. That is exactly correct. Talia, you are a genius. I never said anything different. Let's write that just like that. So you won't like slide everywhere. We're going to write it. Look, no, she's right. So you won't like slide everywhere. That's exactly right. You put sand on the road. Sand on an icy road. On icy road. Again, why would you do that? So you won't like slide everywhere. I mean, like Talia is absolutely correct. That's exactly right. You want to increase friction so you won't like slide everywhere. It's true though. The girl's smart. All right. Next one. What are some examples of increasing friction? Well, we just said one. Sand on icy road. Write that one. Sand on icy road. Salt is more about melting it. All right, here's another increasing friction. Rub them. Rub your hands together. Rubbing hands together. Yep, increases the friction. That's right. Tread on shoes. Sandpaper. Okay. All of those are going to increase friction where you won't, so you won't like slide everywhere. It's true. Talia's smart, man. All right. Mr. Smith has to move a heavy bookcase, and he can't do it without help. What are some ways he could reduce his amount of work? Tell me, Layla. She's a genius. Put some wheels under it, right? Write that in big capital letter. Wheels. Put some wheels on it. You could oil the floor, like to reduce the friction on the floor, or increase the force. Increase force. Get a really strong friend, right? Get a big boy. Yeah, go grab somebody from the sledge horse room. Get the rock to help you. Yes, get a big boy. So you can either increase the force or put wheels. Decrease the friction or increase the force. I'm going to pause this. All right, Miss Kramer loves to hang by her knees on the monkey bars after the kids go home in the afternoon. What forces are acting on Miss Kramer as she hangs? What forces is that? As she's hanging down, what's trying to pull her down to the ground? Gravity. Very good. Gravity is trying to pull her down. Gravity is trying to pull her down. It's trying its bestest to pull her down. All right, next one. An object is traveling at a steady speed in a straight line. Okay, so you've got, draw your graph, and you've got a steady speed in a straight line. What could cause the object to change her directions? Okay, so in order to get it to change directions, you're going to need a force that comes from the opposite direction. Or another thing that would work would be friction, right? If you put something on the ground to slow it down, that would work to slow down the object. Something has to get in its way. All right. Number 12. We're going to describe the relationship between mass and the amount of force needed to move it. I want you to put a marble here, and then I want you to draw a bowling ball here. Zahaya, which one has more mass, the marble or the bowling ball? The bowling ball, that's right. Adam, what's going to be harder to move? The bowling ball or the marble? Very good. Adam, I have another question. What's going to be harder to stop? The marble or the bowling ball? To stop it. If I roll a marble at you and a bowling ball, which one's going to be harder to stop? You're smart, say it. Yeah, that's right. Okay. Bigger it is, harder it is to get it moving. Bigger it is, harder it is to stop, right? Doesn't that make sense? All right. Who's it going to be easier to stop? Kevin Hart or The Rock? The Rock. You can stop Kevin Hart pretty easy. Stopping The Rock is going to take a little bit more effort. Okay. So, right. The more mass something has, the more force it takes to move it. And the more force it takes to stop it. Both of those. All right, so again, I want you to, this next question says, describe the relationship between mass and the speed an object can travel. So again, draw the marble. Again, draw the bowling ball. And then I want you to put Zayden behind them. Hey, Zayden. There she is. Now she's going to push both of them. She's going to push both at the same time. And she's going to push both with 10 newtons of force. Which one's going to roll further? The marble. It just makes more, it makes sense, right? She's going to push them with the same force, and the bigger thing is not going to go as far. The smaller thing is going to go bing. The big thing is going to go boom. Okay, so let's write that. A smaller object moves faster. When pushed with the same force. Very important that you understand that. So it would be much easier to push me than it would be to push that gigantic man that runs the ISS room. What's his name? I don't know. You know, the big guy. Oh, it would be much easier to push me than to push Officer Hill, right? He's a big, tall, I mean, he's a big guy. So the smaller something is, it will move faster when you push it. All right, next one. All right, the difference between the two graphs. This one, trace it with your fingers. It's going up fast, and then it slows down, and then it's at a stop. Do you see it? So this is slow down. Raise your hand if you know the fancy word for slow down. Evan. Decelerate. Decelerate. This one, it was at a stop, and now it is going faster and faster and faster. This is speed up. Also known as, Layla, accelerate. All right. Now, the next one I want to talk to you about, because every single question about speed on your test is going to give you a formula. Highlight the formula. It says here, distance equals speed times time. All you got to do is plug in the numbers, guys. That's it. They're not going to make you guess about what to do. They're going to put it in a little parentheses, just like this. A train travels at a constant speed of 60 miles an hour. How many miles will the train travel in 4 hours? So distance equals 60 miles an hour times 4 hours. How easy is that, guys? So it equals 240 miles. It's going to give you the formula. You're not even going to have to guess. I know, doing math and science. Isn't that fabulous? Doing math in the middle of science. Yeah, I think so. Are we being recorded? Yep, we're being recorded. All right, so the formula will be there. And sometimes it'll be division, sometimes it'll be multiplication, but the formula will always be there. All right, flip. Let's go over here to the next one. We're going to answer 2 more, and then we're going to dance. Because we're going to dance before we get to the review questions. And there are 10 review questions on your test. All right, Anna biked 20 kilometers between 2 p.m. and 3 p.m. Then she rested and biked an additional 20 kilometers between 3:30 and 5. Calculate and describe the change in Anna's speed on her trip. All right, so the first part is, let's look at the first part. She biked 20 kilometers between 2 and 3, right? So write that down. 20 kilometers between 2 o'clock and 3 o'clock. How many hours is between 2 o'clock and 3 o'clock, Jamie? Good. So for the first part of her trip, 20 kilometers per hour in 1 hour. She did 20 kilometers in an hour. Sorry, 20 kilometers in an hour. Then she rested and she biked an additional 20 kilometers between 3:30 and 5. So she did 20 kilometers in 1.5 hours. Does that make sense? So Wyatt, when did she do it faster? In the first part or in the second part? Well, she actually took longer to go 20 kilometers. Yes, This part right here is faster. She went 20 kilometers in 1 hour in the first part of her trip. In the second part of her trip, it took her 1.5 hours to go 20. So this was faster. All right, this is our famous story. Do y'all remember when we did this story graph about the turtle and the hare? No. Or did we do Jaden and was it Jaden and Janie? Who was the turtle? Jaden was the turtle, so he won, right? And Janie was the hare. Well, this is exactly the same. So I'm going to take my highlighter and I'm going to do the turtle first. Turtle never stops, just goes and goes and goes at a steady pace. Everybody do it with me. All right, so this was the turtle. He never gave up. He never stopped moving. He moved at a constant speed. And in the end, he won because he got to the finish line in 15 seconds and the rabbit got there in 14 seconds. See how he got to the finish line in 15 seconds and the rabbit got there in 16 seconds. So the turtle won. Now let's trace the rabbit. He ran, took off fast, beep, and then he stopped. Rested. He saw the turtle was about to get to the finish line and then bing, sped up again, but he was too late. So the turtle beat the rabbit, even though the rabbit had 2 fast bursts right there and there. So here we go. So the story goes, the turtle was constant. He never stopped moving. He went every 5 minutes, he went 1,000 meters. In 10 minutes, he went 2,000 meters and he just kept going. Turtle was constant. But the hare ran really fast. Stopped. Ran fast. And lost. Loser. He shouldn't have given up. You know what happened is he got cocky, didn't he? He was like, oh, I've got this. I'm going to just rest. Yeah, he's like, I'm going to just relax. I don't have to do anything. All right, so we're going to pause and we're going to dance and we'll come back. All right, now we are into the review questions. What is an ecosystem? Ecosystem is the living and non-living parts. It's all of that stuff. Living and non-living parts working together. So it's not just the fish and the frogs and the birds. It's also the wind and the rain and sunlight. Yes. I meant to put non-living. Thank you, Tinley. Miss Ross is a little tired today. Make sure I've got this thing going. I do. Okay. All right, guys, how does pollution move from one place to another? Does anybody remember? Tell me, Zayden. Runoff. Yes. Do y'all remember what runoff is? All right, runoff is when the pollution basically gets washed down from a higher place to a lower place. Runoff from higher elevations, to lower ones. That's it. It just draw a little hill. the chemicals and all the bad stuff just runs down the hill. All right. It just runs down the hill, moves from one place to another. All right, what effect will cutting down the trees have on the organisms that live there? Okay, if you cut down the trees, what's gonna happen, Liam? Thing, that word he used, habitat. If they don't have their house, they live in the trees. You cut down the trees, where are they gonna live? Okay, so it takes away their habitat, takes away their habitat. They will have to move. They will have to move or fight. What do you mean fight? There's one tree. They're all going to be fighting over it, aren't they? They're going to have to move or they're going to have to fight for what's left. That makes sense, right? You and your brother ever fought over a Pop-Tart? Oh, I look, every day is a throwdown in my pantry. Mom, he took the last Rice Krispie treat. Okay, there's one Rice Krispie treat and 4 kids. The kids have 2 choices. Go somewhere else to find another Rice Krispie treat or fight over the one that's left. All right, guys, remember you're being recorded. Okay, yeah, please, because I do not want the kids' parents listening to this and thinking that Ms. Ross is telling y'all to throw down over a Rice Krispie treat. But those are the choices. They can either go somewhere else to find a Rice Krispie treat, or they can fight for the one that there is. All right, next one. Describe how cooking a pot of soup uses 2 different types of heat transfer. Okay, so the pot on the stove, draw the stove, there's the stove. The pot on the stove, that is conduction, right? Because it's touching it. Oh, I'm sorry. So write this on here, it's on the stove, it's touching it, conduction. But then the water, the soup that's inside of the pot, the hot stuff rises, the cool stuff sinks. What's that called? Convection. So there's 2 types of heat transfer going on. You've got the hot stuff rising inside the pot, the cool stuff sinking inside the pot, creating that convection current. The rising and falling of liquids and gases is convection. So there's 2 types of heat transfer: conduction because it's touching the burner, convection because the heat is rising and falling. All right, next one. What must all living organisms do to survive? What are the things that they all have to do? Tell me one thing, Evan. Good. Get nutrients. You get them by eating. Plants get them through photosynthesis. Single-celled organisms get them by absorbing things. Absorbing. Remember, we watched the euglena eat the paramecium. All right, what's something else they have to do to survive? Tell me, Colt. Good. They have to reproduce. Humans do it by making babies. Single-celled organisms do it by duplicating themselves. What else? Good. They gotta eliminate waste. You do it by pooping and peeing and breathing out carbon dioxide. Parameciums do it by opening their cell wall and letting out the nasty stuff. What else, Janie? They ought to grow. You do it every single day. You guys were bigger before Christmas, smaller before Christmas than after Christmas. You grew.
I don't feel like this.
Cells grow as well. What is the last thing that both do? Anybody remember? You do it when you go to PE. You use your muscles. What do you do? What do you do with your muscles?
Exercise?
Starts with an M. Move. All right, these are the things that all living organisms must do to survive. Yes, because if they can't move, how are they going to get food? Okay. All right. Oh, still, you got to chew. You got to move. All right, next one. What are some examples of inherited behaviors? Miss Ross, I don't understand. How can you inherit a behavior? I'm going to give you a hint. Here's one. Hibernate. Does anybody have to teach a bear to do that? Nobody teaches a bear to hibernate. He knows. What's another example of a inherited behavior? Blinking? Yeah, I would say that. Here's another one. Migration. Web spinning. No one teaches a spider to do that. They know. Janie? All of those work. All right, so all of these are inherited behaviors. Well, those are kind of like instinctual. All right. If siblings get DNA from their parents, why don't they all look exactly alike? Tell me, Evan. Well, you get 50-50 from each, but you might get different combinations, right? Okay. So you get 50% from each. But in different combinations. Guys, you're embarrassing yourselves and you're making me uncomfortable. Stop. All right, number 25. Starting with energy from the sun, explain the steps of the water cycle in order. I'm not going to explain the steps. We're going to do a drawing. Here we go. Y'all ready? So draw the sun. There she is, right up there. I like to think of the sun as being a female. I don't know. Because she's the boss. All right, so there's the sun. The rays come down. And the rays hit the water. And it's any kind of water. It doesn't just have to be the ocean. It can be any kind of water. The water evaporates. So this is evaporation. It rises to the air. When it gets up high in the sky, when it gets very high up in here, it cools off. There's cool air up top in the atmosphere. And so it cools off and it condenses into a what, Layla? Good. It cools into a cloud. It condenses and draw the droplets. When you see water droplets, it is most often always going to be condensation. So this is condensation. Then what is it called when the water falls to the ground? Talia. Precipitation. Good. Falls to the ground as precipitation. And then it runs back down to the ocean in runoff. So it goes around and around and around and around and around and around in a cycle. Don't forget to draw your plant over here and label it transpiration. That is evaporation out of a plant. Transpiration is transplantation. Guys, please remember you're being recorded after we finish this. I don't want you to miss a single thing. All right, what is the main function of the nervous system? Cole?
Sending messages to the brain.
Yep, it's the brain. It's about sending messages. The brain is the boss. It controls everything. So, right, control the body. It controls the body. Controls the body. All right. Identify the organisms and draw a food chain using the information below. Remember, arrow means gives energy to. So like if we draw an arrow, that shows what something is giving energy to. Okay, so you've got an ocean ecosystem. There are a lot of green plants which provide energy to fish. So start with plants. And their energy goes to fish. And that's small fish. So the small fish eat the plants. The energy from the plants goes into the fish. Then the large fish get energy from the small fish. So the energy transfers again. The small fish, the energy from that goes into the large fish. Humans go fishing and they want the largest fish they can find because larger fish provide energy for more people. So the large fish are caught and they're eaten by the humans. What did I do wrong? Large fish goes into the humans. Okay, so this is the flow of energy. All right. And I think that that is it for today.